So the properties of water that are particularly important for life include the fact that water has a very wide temperature range.
Oh gosh.
Liquid temperature range. How many degrees?
Oh
100 degrees Celsius, right. It goes from 0 to 100 degrees. 0 is the freezing point. What's the melting point if 0 is the freezing point? 0. Water boils at 100 degrees Celsius. What's the condensation point of water? 100. This when we talk about melting points, freezing points, boiling points, etc. It all depends. It's like a border going from one state into another. It's the same thing, but it's different. You know, if you're coming from Georgia into Florida, or Florida going into Georgia. Same thing if you're going from a liquid to a gas, or from a gas to a liquid. That conversion, both of them occur at the same temperature. Okay. So that's important. That's a wide temperature range. Liquid form is not really a popular form in nature. If you look at most of your elements, they're either solid or gas. Most of them are solid. So this is true of many different things on Earth. Of course, the bulk of the Earth is solid. Well, it's kind of a semi-solid when we talk about the mantle, but a lot of it is mostly solid. And then you have the atmosphere as a gas. But water is unique in its polarity and its shape, and these are some things that we don't need to go into detail now, but you may know that it sticks together real well. And also because of it has a funny Mickey Mouse kind of shape to it, with the oxygen and the ears or the hydrogens, it doesn't fit together that well into a nice crystal structure. So it tends to stay liquid for a long time because the molecules stick together, but they don't tend to assume a set ordered structure that easily, and that'll be part of another property of water that makes it important. So that's good because you can imagine that you're going to want to have water in your cells, or liquid. Excuse me. You want to have a liquid substance in your cells. You can't imagine, life forms that have solid cells or gaseous cells for that matter. All the chemical reactions and things that need to take place, and the fact that you kind of need to stay all together in one piece and be flexible and those kind of things. So liquid is ideal, and since water is liquid over wide temperature range, and it's mostly liquid in the temperature ranges that we find on Earth naturally, that's a perfect fit for having it be a substance that supports life on Earth, and pretty much anywhere else as well, for that matter. Another property is the fact that it has a very high heat capacity. Okay, that means that it can absorb a lot of heat energy without much temperature change. And so this particular property was preparing life on the Earth for life before life was actually even here. So theoretically, Earth was here first, and then life came later. But the presence of water being able to cool down the surface of the Earth very rapidly, and then spread the heat energy from the sun around the globe, have made the temperature have a much more moderate temperature range. You see on other planets 100 degrees plus temperature difference between night and day. That's not conducive to living. Things can adapt to extremes, but they can't adapt from a day-to-day basis, or it's very difficult to do that, as you can imagine. So water, of course, water absorbs a lot of heat energy and moves around through currents, which we'll look at later, and therefore distributes the energy from the sun. And originally, a long time ago, it also cooled off from the heat of the formation of the planet itself. And so those are properties. That's one of the properties of water that's extremely important when it comes to life, and it's the ability of water to support life. Okay, so a solvent. Solvent means it's something that dissolves, a liquid typically that dissolves something else. And water dissolves ionic compounds like salts, iron compounds, and phosphorus and calcium and nitrates and all of those other kinds of things that our body needs and plants need, etc. And it also dissolves many, not all by the way, not all ionic compounds either, many polar compounds. Sorry, group, who was that? Two. Sorry, group 2. But covalent compounds can be polar or nonpolar. Organic substances are covalent. Many of the organic substances are nonpolar. Water does not dissolve those, just like water does not dissolve oil. Oil is a covalent compound. And it can dissolve ionic and polar ones. because water itself is polar. That means it has a positive and a negative side. And sugar is another example of a polar compound. And because the charges on the water molecule can break apart the charges that are holding the sugar molecules together in the crystal, or the salt molecules together in the crystal, etc. So this is very important for all cellular organisms, from bacteria on up to us, because that's the way we bring food into our cells, is by dissolving it in the water that either for our case, in our blood, but in the case of single-celled organisms, in the water that's around them. And it also is the way that waste products are removed from the cell, by water coming out of the cell and dissolving the stuff that needs to come out and excreting it. Okay, so that's why the polarity of water and its ability to dissolve a wide range of compounds is an extremely important facet to that. This is also why, for example, like I said, water liquids are relatively rare, but there are a lot of organic liquids, oils mainly, and alcohols. So you could theorize that would make a good cell, but they don't dissolve ionic and polar compounds. So those substances could not bring food into the cell, because the food has to be dissolved, it has to be broken down into individual molecules. And the same with waste products coming out of the cell. Okay. Now finally, water expands upon freezing. Very unique property. Most substances, when they go from a liquid to a solid, they condense, they become smaller. And as a matter of fact, water, like most substances, as you cool it down from, let's say, for example, 20 degrees Celsius, it does get smaller and smaller. 20 degrees Celsius water is less dense than 4 degrees Celsius water. But I picked 4 degrees because 4 degrees is actually when things start to change. So when water hits about 4 degrees Celsius, it has to, remember I said the molecules are like little Mickey Mouse heads? They have to line up. The oxygens have to line up with the hydrogens, and it's funny shaped molecules. So what happens is they all line up and end up lining up in a hexagonal pattern here. This would be one, and then one over here, etc. I'm not going to draw it out right now. But the point being is that they have to spread apart, so there's a lot of empty space in here, molecularly speaking. So they expand, they get bigger. That means they come up. So this is important because theoretically, without this particular property of water, the oceans would freeze from the bottom up. Because, of course, water gets colder as you go down. And then also pressure usually will freeze things, except for water. But pressure will push those molecules together and help that become a crystalline structure. But it has just the opposite effect on water, because the water molecules, in order to make that ice crystal, they have to spread apart. So ice crystals won't form under high pressure. And also, as water cools down as you go down and get deeper in the ocean, because once it hits 4 degrees Celsius, as it cools down, it starts to expand. Even before it freezes, that water expands and is lower density, so it floats up to the surface. So you actually also have this constant currenting circulation pattern of the water as it cools, expands, floats up, and goes through the whole process all over again. Okay. So that's a real good property that keeps the water from doing something that other liquids would do. This is not really necessarily good for life on its own, but it is good for, it does, like I said, keeps the oceans from freezing over. And we see some other examples of frozen over planets. Not planets, but Europa, which is a moon of Saturn, I think, maybe Jupiter. I don't know, somebody can help me out there. But it's covered in ice, and they theorize that there may be a liquid ocean underneath it. Water, because only water would do that. Only water would form a solid part with a liquid part underneath. So that's due to its particular properties. All right, any questions about the physical properties of water and their importance to life? So that's really covers both 3 and 4 here, for the most part. Quickly we'll look at distribution. This just is where water occurs around the world, and also how it moves through these different areas that we find it in. Now, it's probably, hopefully, no surprise to you that most of the water, 96.5%, is in the ocean. And then the second biggest collection of the compound H2O is in your ice sheets, glaciers, sea ice. Okay, the national exam does ask about that for some reason. And the reason why I say for some reason is most discussions of the hydrosphere don't count ice. The ice on the Earth is something called the cryosphere. But, like I said, on the national exam, they like to include that in there and ask about it. So I want to give you that data to make sure you understand that. Now, this is fresh water. Ice is just because ice does, ice does exclude salt as it freezes, and therefore sea ice is fresh water. But that's not something I want to stress here, salinity of these different things. Because, for example, we have saltwater lakes. The third biggest collection of water is groundwater. Some groundwater is salt, some is fresh. Actually, most of groundwater is salt. The closer you get into the interior, it becomes more fresh. So, but that's where the majority of liquid water outside the ocean is in the ground, underground. Then you have your surface water. These are your lakes and rivers and those kind of things. Now, keep in mind when you're thinking of these things, their connection, it all is linked to the hydrologic cycle, which we're talking about here. The oceans, of course, containing the majority of the water, most of the evaporation comes from there. There's evaporation. And then we get precipitation. Also with evaporation, you get transpiration from plants. And then you get your condensation of clouds in the atmosphere. Then it precipitates down. And when it does that, when it comes down, it's going to settle on the ground. You remember our three processes. One of them was what do we call soaking down into the ground? Infiltration. Very good. Okay? So that's where we get our groundwater. Okay? The other thing, and by the way, that groundwater is flowing out towards the ocean to start the whole process all over again. Some of it will not soak down to the ground. It will run off and collect into our surface water due to gravity. Some of it, of course, is going to evaporate and go back up into the atmosphere and condense and become atmospheric water. So that's the connection between what we call the collecting areas or sinks. Here's a term here that if you're not sure what I'm talking about here, that just means where things collect in a cycle, in this case a water cycle. So you've got the cycle, you know the water cycle, hopefully by now, it's an elementary school concept. But there's some details that we've added in here, perhaps, and these particular processes show how water transfers in through all these other things. And that's all very important for life because a couple things. First of all, the evaporation condensation process transfers heat energy and precipitation down, all that does as well. Then the process, once the precipitation does go down of running off or soaking down in and dissolving things back here, distributes nutrients. That's how we get a lot of the fertility in our soils and stuff and everything is from that, the water cycle process doing that. We'll look at the rock cycle and see how that's important. And then finally you've got the whole process starting all over again, forming the clouds in the atmosphere and things like that. And if this also distributes the energy, distributes nutrients, and provides fresh water. Because things on land need fresh water, and of course that's a natural purification process that goes through. So here's your different processes, here's the different collecting areas. Any questions? I'm going to go into some more detail about groundwater, particularly like the Florida's groundwater, next class. But let's go ahead and move on to currents. Like I said, water has a high heat capacity. This is important for energy distribution, and that energy that the ocean distributes, the water distributes around from the sun. I'm not going to take thermal, I'm sorry, because actually the energy from the sun is not thermal. It's only thermal once the water absorbs it, so we're going to call this solar energy. But anyway, it does that through currents. So you have two types. You have shallow currents that are driven by the wind. Okay, the wind follows certain patterns. We'll study that when we study the atmosphere. But as it blows across the surface of the ocean, it's going to push the water that's underneath along with it. That's where the Gulf Stream comes from. Then you have a lot of these deep currents that are caused by changes in density. Density changes are related to differences in temperature and salinity. So things that are going to happen as water moves around, as you have evaporation, precipitation happening from it, as it goes from tropical regions or from equatorial regions to polar regions, that are going to change the temperature of it. So if it cools it, it's going to make it more dense, as well as the salinity of it. So if it becomes more salty, it will become more dense. And when things become more dense, they sink. So that water sinks down, travels along the ocean floor, comes up in certain areas, pushes up against continents and stuff, and as we'll see when we look at the biology of this, that brings a lot of nutrients to the surface. But all those together, all those patterns together, and I'll show you a diagram if we have time, are what we call an ocean energy conveyor system. They're all connected, and it distributes energy, nutrients around the globe. Okay.
Oh no, my pencil almost fell.
Oh, okay. Sorry to hear that. All right, so these have a big influence on weather patterns. That's fine. Kinetic energy. It is kinetic energy, group 7, so I'll give you that. All right. And weather patterns, I'll take that as well. Climate is actually what we're going to talk about. And so next time we meet, we will talk about how these ocean currents influence climate. And look at some diagrams and things. Any questions about these 3 parts here?
What about that one?
Well, did I miss one?
That right there. Deep is correct.
Deep is correct.
Okay.
Yeah, shallow deep. Okay. All right, let me double check. Everything up there is correct.